was working on, and this is supposed to be just a kind of an interlude, and well, here's what I started with. So I wasn't really happy with that, and I kind of felt like there was nothing there for listeners to grab onto, and it's just not really what I wanted. And I thought about these repetition examples and thought, hey, let's just do that. What if I take each measure and play it twice, so I end up with fewer measures, and definitely more structure. So you can hear what that sounds like. So to me, whether that's better or worse, it has a much stronger character and overall structure due to this repetition. What happened here? Okay, so let's talk about repetition and structure in deep learning systems. One question is, does structure learning even take place? And certainly, if you listen to a lot of examples, especially symbolic music composition with deep learning systems, sequence learning systems with vector quantization models or transformer models, you can hear structure and repetition, but it seems to be mainly at smaller timescales. And sometimes researchers will get the machine to compose 4 bars or 8 bars and then repeat it twice. And in a creative field, anything is fair game, but we need to be careful about evaluation, because it may be that the most musical and structured thing is not the content, but the fact that the researcher decided to play it twice, and you heard, what a dramatic difference that makes. So, if anything, repetition in these systems, at least past systems, is largely missing in deep learning-based music composition. However, more recently, I really need to change this and say that repetition was missing, particularly in symbolic deep learning-based music composition systems. And the reason I would say this is that it wasn't too long ago that systems Suno and Udio came out, and if you listen to the music that they produce, it's clearly structured with very orderly, conventional popular music, 4-bar and 8-bar phrases, lots of repetition, lots of sections. You'll hear a verse and a chorus, and we'll go back and repeat the verse almost in the same. And so, very clear structure and repetition, and we'll talk about that a little bit more later. But why is repetition hard? Why didn't the earliest sequence learning systems learn to repeat things, since it's so common in music? And we'll talk more, actually measure how common it is in a moment. But let's assume that's the case. Then one difficult thing is just the level of abstraction that it requires. And this is just speculation. I don't have a proof that this is more difficult to learn, but it just intuitively seems like if you're looking at specific pitches like G, F, E, D, and what comes next, well, it's likely to be followed by C, because just listen to it, da 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 is going to happen next. And you can learn these specific sequences pretty easily. It's just like learning word sequences. Gabe has this dog a drink of, what comes next? Well, probably water. But on the other hand, to learn how to do repetition in music, it's a more abstract problem because you're really learning something like there exists an arbitrary sequence X such that XX occurs in the music sequence. And X may be something, some music melodic pattern that's totally unique, that's never occurred in music before. And so you can't just learn from examples all the possible values of X. You have to know the concept. And so in other words, it's not enough just to learn concrete patterns the way we know that sequence learners are capable of. So the second problem is to do generation with repetition. I would claim requires three different activities. One is you have to plan at a kind of higher structural level, like XX, not in terms of individual pitches. And then you have to create the material, what is the material that goes into X that you're going to repeat. And then finally, you have to have a copying or imitating activity that's a little bit different from the original generation or compositional activity. And whether or not a deep learning system can integrate all these three activities, and basically maybe in the learning stage you have to kind of disentangle these different activities in order to really understand how to compose music. I think that's part of why this seems to be so hard. So this is, so far it's a lot of hand waving. I've made a lot of claims about music and structure here that are certainly not new. It's no news that music has repetition. And the question is, can we support these claims with data analysis? And there are lots of ways to do that, but I think we've done some interesting work in that direction. So the first thing to think about is, and we're going to talk about now specifically about popular music, because I think it's easier to analyze, obeys enough conventions that it makes, that you can find a lot of examples that are kind of all based on the same approach and the same processes. And so most of our work has been working with the Pop 909 data set, which is around 1,000 popular songs from China. These songs are pretty conventional and pretty Western sounding, aside from maybe an emphasis on pentatonic scales. Otherwise, they're pretty Western. So I think everything that I say about Pop 909 applies to Western, and we have some smaller data sets that confirm that. Anyway, so in popular music, structure, oftentimes people try to relate structure to features in the music. So for example, we say that phrases end on longer notes, or phrases end on tonic chords or tonic pitch. Melodic phrases have an arch form. Phrases are performed faster in the middle and slower at the ends. And so these are kind of rules of thumb, and they're all basically true. But if you want to really study structure in music, there's a problem, because we don't know if this is all interrelated organically, or do features result from phrases, or do we just define phrases in terms of features? I mean, we're certainly influenced by features if we're hand labeling phrases. So we can't really say how features are determined by structure if the structure itself is defined in terms of features. And that gives us results in a lot of circular arguments and kind of confounds in data. And so we would like to break this cycle. And so what we've been one of the things we've done is study structure arising strictly from repetition. So we ignore features and these rules like phrases end on long notes. We're going to develop phrases in a completely independent of duration manner, and then we can ask, is it true that phrases really end on long notes? So how do we define structure based on repetition? Well, we think of music structure as a kind of data compression. And so imagine these lowercase letters represent measures. So we have a very strange piece of music here with the 3 measure phrases, ABC, 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 ABC. Lots of repetition there, so we could rewrite that as ABC, ABC twice, or just simply ABC repeated 4 times. And so we've got 3 different representations of the same thing. We can flatten it and write it all out. We can think of it as something repeated twice or something short repeated 4 times. And the question is, from a data compression standpoint, which representation is the shortest? And the answer, of course, is the last one. And so we say that is the structural representation of the music. And there are some cognitive psychology bases for talking about data compression and most simple representation. But this is not a cognitive model. This is just a pure data model that allows us to do things objectively. So we rewrite the music as sequences of measures that we call phrases, and we use upper. So the lowercase are the measure denotes similar measures, and uppercase denote similar phrases. So we can take a song form like ABCD, ABCD, EFGH, ABCD, and rewrite that as AABA in capital letters. So that's pretty standard, familiar stuff. But it's interesting. Like, we don't have to do this by hand. We can derive this from these by just optimizing the data compression. And then once we do that, we notice very often we get structures like this. This is phrase A followed by B followed by some bridge material X, and then that's not repeated anywhere else. And then we have a repetition of A and more bridge material like Y, and then 2 repetitions of B. So we use the presence of this kind of unique bridge material to form a higher level structure. So we call these things sections. So in this case, the capital A, capital B, those two phrases form one section. Capital A is another section, and BB is yet another section. And it's a little bit arbitrary, probably doesn't work a lot of times, but it's an objective way to form a second level of hierarchy, and then it remains to be seen whether that's meaningful or not. So let's see what we can do with this kind of structure. First thing we looked at was harmony. We looked at chord distribution across different across phrases, beginning of phrase, end of phrase, middle of phrase, end of section, and so on. And so one thing is, so this graph is showing the probability or the frequency distribution of different chord types. So this is Roman numerals, 1 chord, 2, 3, 4, 5, and 6. And you can see that overall, so background represents just every chord in every piece. Overall, the 1 chord is the most common, but not a whole lot more common than 5 chords, and all the chords are kind of in a pretty narrow range, pretty flat distribution. However, if we look at the start of phrases, you can see the one chord up here is way more common than anything else. And so immediately, we can see that there's some connection between harmony and this repetition structure. We can also compare different levels of hierarchy. So if we go over to the last two categories, we can see that if you're within a section, so remember the sections are these groups of phrases with bridge material between them. So if you're within a section, interestingly, the 5 chord is actually a more common phrase ending than the 1 chord. But when you get to the end of a section, which is also the end of the phrase, but the last phrase of a section, then suddenly the 1 chord is way more common than the 5 chord. And so this is showing evidence that this designation of 2 levels of hierarchy, in a particular kind of quirky definition, ad hoc definition of phrases in terms of bridge material, it actually plays out in the data and has some correlation with harmony. Well, that's interesting. So let's go look at melody and let's go look at rhythm. And everything we've looked at so far actually has significant interaction with phrases and with sections. So all of this stuff is significant and important. So we conclude that there's at least 2 levels of structure, and they are, if you want to compose music in a human-like, if you want music to sound human-like and to be human-like with human-like distributions, then you've got to have repetition structure, and you've got to have some correlation between that structure and all the elements like harmony, melody, and rhythm. So that's pretty interesting. And note that these results do not depend on any human judgments. We're not hand labeling phrases or any other features. So this is all objectively computed. So there's lots of more work we could do in that direction. But I want to, let's see, I thought, no, okay, right. So let's move on and think about another feature, which is entropy or cross entropy and how that relates to repetition. So this is kind of led to another series of studies. So this is really about, motivated by thinking about prediction in music and, how predictable is music and how does predictability relate to music and music structure. And in particular, we've been using the variable order Markov model to help us, as a model of predictability of music and sort of a model of music listening. And it's interesting because for 2 reasons. First of all, it's particularly good at sort of capitalizing on repetition. So it's finding repetition and using that to make predictions. And so really prediction and cross entropy in this case are essentially the same thing. Cross entropy is just a numerical way to evaluate the quality of prediction. And that in turn is a good way to measure amount of repetition. Another important thing, let's see, I'd love to spend time explaining variable order Markov models in greater detail, but there's not enough time. So let me just say, if you're not familiar with them, variable order Markov models are derived from Markov models, and the basic idea of a Markov model is if you want to make a prediction, you assume that the next thing in a sequence is related to the current thing in the sequence, and maybe the current thing includes the current and the previous, or the, some n previous elements of the sequence, which we call the prefix, and then the question is what comes next. And you guess what comes next, or you predict what comes next based on all the observations of that prefix in the training data. So variable order Markov does the same thing, except that if you try to use a very long prefix, the data becomes very sparse. Like how, for some sequence of, let's say, 8 pitches, how many times are you going to find that exact sequence in the data set? So it's not very good for estimation unless it occurs in the training data. And so what you could do is look at, and if there are not enough occurrences to make a prediction, then you can back off from length 8 to a length 7, 7th order Markov model. And then if that doesn't work, you can back off again to a order 6, and you keep going to lower and lower orders until you find some support for it in the training. So that's basically how variable order Markov models work. And the most interesting, well, for our work, a very interesting thing about these models is they're very cheap to train. So in fact, you can update the model at every time step as you're making predictions of a sequence. So you make a prediction, and then the right answer is revealed to you, and you can incorporate that revealed data into the model to make the next prediction. The other, well, I think I'm going to skip this slide on cross entropy, but this is just about the idea that at every step or every prediction, you're really predicting a probability distribution, and then cross entropy is the way that we use that to sort of quantify how good the predictions are. So we're making predictions with variable order Markov models, and we're measuring cross entropy to see how good those predictions are. And we can produce some interesting graphs. Like this is after dividing the music into phrases, so thousands and thousands of phrases. If we normalize the phrase so that 0 is the beginning of the phrase, 1 is the end of a phrase, and let's see how, on average, how does the cross entropy change across the phrase. And what you see is, on average, we have this decrease. This is not huge. This is not a zero-based label here. So we're going from cross entropy of 4.2, and this is measured, think of this as measured in bits, from 4.2 to a little less than 3, so a little more than 1 bit. But anyway, it's interesting because if the entropy is lower, it means that there's repetition helping you out. And so what this is telling us is that even within phrases, there's a certain amount of repetition that helps these variable order Markov models. Another thing we can look at is just entropy in the same way that we looked at other music features like chords, harmony, and duration at beginnings and endings of phrases. We can do the same thing with cross entropy and say, okay, so on average, like the cross entropy is 1.5 across all notes, but at the beginning of phrases, the cross entropy is 3, significantly higher, and so we see different amounts of predictability at different points in the musical structure. Another thing that's really interesting about this, I think the most interesting thing for me, is conventional wisdom is that you get better prediction if you have more training data. But here's what happens in our case with music. If if we train on pitch sequences across this entire data, so it's about 1,000 songs, tens of thousands of notes, we can build a variable ordered Markov model, and if we just fix that model and apply it to any given song, I guess you hold the song out and train on every other song, and then use what we've learned to make predictions within a song, then we get this solid blue line. And notice that suddenly, well, this blue line is much higher than the orange line. So what's the difference here? Well, the orange line is using only the song itself to make predictions, and it's completely ignoring, the 1,000 other songs in the data set. And so what this says is that a song has better information to predict the song than thousands and thousands of other notes from other songs. And that's kind of contradicts this idea that more data is good for learning. And it's just saying that songs do not predict other songs very well. And when I talk to a very accomplished songwriter about this kind of surprising finding, and he said, yeah, when he writes songs, he even has friends that are like encyclopedias of songs, and he'll take a phrase that he's written and send it to his friend and say, does this remind you of anything? And sometimes the friend will say, oh yeah, there's this song that you never heard before that is kind of similar, and then my friend will say, okay, I can't use that, or I'll manipulate it to make it sound less like some existing songs. So composers consciously strive for unique sequences, and so if you're trying to use a sequence model to learn how to write sequences, there's something wrong there. All right, so this graph comes from looking not at single phrases but entire songs. So this is beginning of song is at time 0, ending of a song is at time 1, and we can look at how the average cross entropy changes from the beginning to the ending. And now we look at the graph here. This is cross entropy 4.5 at the bottom, which we see at the beginning of the song, and it gets lower as you go higher. So this is more predictable is this upward trend. And the blue line is average cross entropy. And so you see this really interesting thing that it starts upward almost immediately. So repetition is happening very early in the song, and it's making it more predictable. And then about 20-25% of the way through the song, suddenly it's getting less predictable. And I'm pretty sure that that's just because at some point in a song, like you typically start with a chorus or a verse and then switch and do something differently, and that makes it less predictable for a bit, and that's this little dip we see here, and then you learn that, and then and there's more and more repetition until about halfway through the song you basically played everything, every sequence has already happened once, and so there's nothing else to learn. It's very predictable. Entropy is only about 1 bit per pitch, and it stays that way until almost the very end, and then there's a little new material at the end that's causing a higher entropy. And this relates directly to the amount of repetition, which we can measure in a different way and get the green line. So you see there's high correlation between repetition and cross entropy, or I guess inverse correlation. The more repeated things are, the more predictable they are, and the lower the cross entropy. Okay, so now we can compare what we find in human-composed songs to what we find in machine-composed songs. And so this is one example of comparing, of measuring, doing the same cross entropy experiment with some music generated through deep learning. I think this is through a transformer model. And you see a different kind of curve. I mean, first of all, it's a lot slower in starting to ramp up. And that's because it's just, generating lots and lots of new material at the beginning, when it should be, a human would immediately start repeating. There's never a point where what's been done is changed to, present contrasting material like a chorus or a verse. And so we don't see any dip in the cross entropy curve here. And the other thing is, it seems like the model is constantly introducing new material, but sort of less and less new material. But at 50%, there's still enough new material that the entropy is still hasn't flattened out to the bottom yet. Different. It just shows that things are not structured in the same way, and we can analyze that in different ways. So, for example, this is looking at entropy at phrase endings in Pop 909 versus looking at phrase endings in deep learning based music. It turns out the deep learning based music wasn't even really parsable into clear phrases, because there just wasn't nearly as much repetition. And so we kind of cheated and said, okay, well, let's just pretend that there exists some 4-bar phrases or 8-bar phrases, and see if we can detect any change in entropy. And you see basically that it doesn't happen. So the conclusion here is human songs generally have lower entropy. This green curve is humans and it's lower. And human song phrase endings are distinctly different, much more predictable. Okay, so I said I would get back to talk about Suno and Udio. So it seems like there might be a counter argument to my claim that deep learning is not learning music structure, and and the first thing I'll say is that even that is a negative result. Like you can't say that this kind of learning is impossible just because you tried it and it didn't work. So that's not very scientific. And so, sure enough, more recently, Suno and Udio have come along, and they do exhibit a clear repetition structure, at least through, by informal listening and observation. So you have to wonder, at least I really wonder, how are they doing this? Is it just because they have more data? Is there some engineering or some kind of cheating, or just better architecture, inductive bias, allowing Suno and Udio to learn structure? So, for example, we know that lyrics are marked in, I know at least in Suno, with chorus and verse. So there's kind of a hierarchical marking of lyrics that are conditioning the music generation. And so, it's conceivable that that's enough prompt to learn when to use repetition. I really don't know what's going on, and these are not open or documented systems, so we don't know how they do what they do. And I think there's really interesting room for research there. And in fact, one of my former students has been building a kind of open source model of Suno, and he says that the audio tokenization creates shorter sequences, and these shorter sequences are giving rise, allow the models to learn about repetition. But by that argument, it seems like the symbolic learning systems would be even better, but they're not doing it. So that's are open questions. So just to wrap up, we need to understand more about music, and particularly the role of structure. Structure can be used in AI to compose music, and we have some examples I didn't even talk about of kind of symbolic systems that combine some deep learning and some rules to incorporate structure that are pretty effective. We can create music without hierarchical structure, but the results are rated lower in quality. We've done listening experiments, subjective evaluations to show that that's true. So structure is really important. Repetition and information theory give us objective ways to analyze music structure and repetition, and I think that's one of the most interesting things that we've been able to do is just formalize all of this stuff. And knowing more about the role of structure in music, maybe we can bias learning algorithms to pay attention to structure and learn to use it. And maybe that's what Suno and Udio are doing. Maybe they found other ways to do it. But one way or another, I think structure is a really critical element of music that deserves study. And so I'd like to thank all of these people that were involved one way or another in the stuff that I talked about. So I'll leave it there, and maybe we can take some questions. Anyone?
Great talk, Roger. Thank you so much. I thought it was really interesting to see that for the variable Markov model that it didn't really work as well when it was going across songs. I'm sure you've heard of like idiom.
Yeah.
Yeah, so idiom is like kind of a surprisal or complexity measure for music that works in the symbolic domain. But there's also the dynamic regularity extraction model. I'm not sure if you've heard of that one. That's like a Bayesian inference model. It's basically like a detector of auditory salience. So it's not specific to music, it's for anything, where you feed it a set of features and then it carries out some Bayesian inference, or some Bayesian models on it. But basically what you, like, in our lab, we've found that you can actually align, or like it's actually aligned with human perception. So there are perceptual qualities that you can extract from music and then feed it to the model, and it'll actually tell you like, how surprising or complex a song might be overall or over time. And I think it's interesting that you found that with the variable hidden, or the variable Markov model, because things like idiom are trained on a corpus, whereas D-Rex is not. It's just like whatever it's experienced before like the current slice or whatever that you're analyzing in the moment.
Mm-hmm.
So I just thought that was really cool, because I always thought like, oh, maybe idiom is more realistic or more aligned with perception because it's trained on a corpus, whereas maybe it really is just like based on what you're hearing in the moment. And of course, like, I think it's different for like, if we're talking about individual subjective complexity or surprisal, because then maybe you want to train it on the corpus of like all the music that you have in your library to then detect like how surprising or complex something might be to you as an individual, which I think is a really interesting point for like music recommendation systems and stuff. But I just kind of thought it was cool that supported the D-Rex model as well, because the D-Rex is audio, so it's really nice to just be able to feed it the features from audio as opposed to needing to have like MIDI for anything. But yeah, it just, the novelty and complexity kind of goes with all this entropy stuff, so I thought that was an interesting connection.
Yeah, and I think maybe one way to look at a lot of the stuff we've done is this is sort of like idiom applied to pop music, or sort of crossed with the ability to automatically derive some repetition structure from pop music, and then see what you get. But yeah, we certainly, yeah, I think the idiom yeah has a lot of interesting things. And another thing that sort of influenced my thinking is David Huron's book on anticipation in music. And one of the interesting things there that he spends a lot of time sort of speculating on is that that our brains are doing different kinds of anticipation and prediction. So he believes in I mean, in his model includes the idea that we have some really, low level kind of audio surprise detectors that even release adrenaline or something into our systems at a very low level, before the sound even gets processed at higher cognitive levels. And so he thinks that some of the enjoyment of music is related to kind of lower levels inducing fear and surprise, and then higher levels explaining it away and saying, oh, if only you had waited another 500 milliseconds, this higher level structure prediction system would have said, of course, that was going to be surprising, and so I think that stuff is really fascinating. I think there's so much more to learn.
Yeah, really interesting. Again, thank you so much for the talk. It was really great. I may be reaching out individually just because I think that there's some interesting things that we could discuss regarding these projects.
Sure. Yeah. Thanks for the comments.
Yeah. Thank you.
I got one. Or yeah, I'll go over here so you can see me. I was just wondering, who is the student you were talking about that's making an open source model of Suno/Udio?
Oh, it's Ruben. I'm blanking on Ruben's last name.
No worries. That's really cool that he's doing that. I mean, like, I guess just thinking about that, I know a couple other people who are doing similar stuff or trying to make open source models in this vein in response almost to what we've seen over the last few months. And we're doing some research of our own trying to make a generative music model. I'm wondering what you think the limitations are to, that we might run into based off of what you've found so far.
Oh, wait, in terms of building a Suno-like model?
In terms of even creating the framework for one, yeah.
Yeah. Well, one thing is it's not clear to me how much data you need, but I think it could be an awful lot. And so, I worry about the GPU time. And I mean, first of all, they've all been sued for copyright infringement because they're clearly training on lots and lots of copyrighted material, and maybe that's okay for us to do as researchers. It makes it possible. I mean, it's going to be a problem, to publish the work or to push models out there. So that's one thing you might think about, that even if you can do it, how are you going to share this scientifically? And that's something that Ruben has been worried about. And it's Ruben Yuan, by the way, and I'm pretty sure he's in Hong Kong now.
Okay.
um, but anyway, okay, so the computation time, how do you disseminate the results, how do you evaluate the results
Sure.
is are all tough questions. Um, yeah, and then beyond that, I guess I'm kind of, I have mixed feelings. Partly I feel like if you just do it, it'll probably work. But on the other hand, there's a lot of evidence that I show that kind of indicates it shouldn't work.
Yeah.
And so I wonder, are there some secrets in there that you might or might not stumble into, and so I think you're not guaranteed to have success.
I mean, that makes sense. I know, like, some other researchers I've been talking to in this field are very skeptical of what Suno and Udio actually did. Just because, like, I'm quoting them here. They were like, the research, if you look at what it's actually capable of, does not seem that impressive. It's just very amped up, probably because of the copywritten data. I actually wrote a paper on that a couple days ago for a class, the lawsuits. So that's really cool that you brought that up too. But I mean, I think it makes sense, especially with like the way that training should work. It makes sense that it shouldn't, but it's very interesting that it does, or at least it does in this consumer base.
Yeah, I think a lot of, from a composition standpoint, I think a lot of people are, it's one of those things where, the more familiar you get, the more disappointed you are, because when you first hear it, you hear lots of new things and things that, you wouldn't expect, and you say, wow, this is amazing. And then at some point, not too many songs down the line, you kind of feel like everything that it generates has this very strong UDO quality, maybe.
Yeah.
It's kind of like when FM synthesizers first hit the market, people were just astonished because like the Yamaha DX7, for example, has all these presets and it makes all these different sounds, and
Right.
it's incredible, and people would say, oh, that slap bass sound is so good, and the string sounds are so good. And then after about 2 weeks of listening to it, you start, like, your brain figures out the common thread of FMness that permeates everything that comes out of a DX7, and then it becomes like very recognizably FM, and it wasn't really so good to begin with. And I think UDO might be like that too, that if you listen to it enough, it's going to be, okay, this is not really fresh creative pop, it's pop music that's permeated with this UDO-ness, style or feature or something. And but on the other hand, that you could say that about almost anything in machine learning, and people say that about many successful composers. So
I mean, it's true, sure, to a degree, right? It's like like there's a give and a take. Everyone's got their opinion about it. It's also funny that you mentioned the synthesizer thing, because I don't know if you can tell from the room we're in, but we're in NYU Synth Lab, so there's probably an FM somewhere in this room.
Yeah. It looks like a lot of fun toys there.
Yeah. Thank you.
Yeah. I was going to say, just there are surprising things going on in UDO. For example, there was something I was listening to that had some like an audio delay effect, but it's pretty. I'm pretty certain that they didn't actually apply an audio delay. It was like the sound of the delay was computed by the deep network.
Oh, wow.
And these delays were actually echoing words from the singer or from the chorus. So you would hear those words, and they were at a fixed one measure later or 2 beats later or something. So it was kind of like beat synchronized delays, and I thought it was kind of shocking that somehow we're dealing with tokenized audio, and yet somehow there's some levels of abstraction that are computing these audio tokens to include the result of adding reverb and delay and audio compression, and I'd love to know more about how that works.
I think many of us can agree on that front. Everyone's trying to crack the box.
Yeah.
Anyone else?
Yes. Thank you, Professor, for a very interesting talk. And I do have two questions. First one, I'm more interested in, can you give a brief, discussion about how you were labeling the data in the first structure study that you described about how are you labeling the data, how are you preparing the data set, because as far as I know, Op909 doesn't have the structural labels, and you said that your algorithms learn those structure labels by their own, but also I was looking at your paper, and then you have this notation based big A's and small x to denote melodic and non-melodic sequences.
Yeah.
That was question one. The second question is that I would presume a lot of people rely on their perception of structure based on melody lines, let's just say the general public, instead of maybe more trained musicians who are trained to identify chord progressions, but the general public may be to say we can denote some sense of structure based on melody line alone. So what if we mess up the chord, keep the melody, mess up the chord, mess up the rhythm of the chords, and will the computer still be able to denote the structure based on what you have designed for it?
Yeah, okay, so first let me tell you what we did. So Pop909 is quantized. I mean, there are, the beats have been very carefully, well, first of all, Pop909 is human transcriptions of pop songs, and so they're cleanly separated into bass, piano, accompaniment, and melody, and these are done with quantized MIDI, so you know where the beats and the bar lines are and everything. So it's easy to parse or relatively easy to parse it into individual measures. And then what we do is we consider two measures to be the same if the melody is similar, the chords are similar, and the bass line is similar. And we have some kind of simple similarity metrics for comparison, and they allow a little bit of variation. So there are some thresholds that are kind of arbitrarily determined and used to determine if two things are the same or not. But ultimately, we come up with kind of a binary decision. This measure is a repetition of some other measure or not. And and I should also mention that there are chord labels in Pop909 as well. And so after we decide which measures are similar or not, that we can effectively, that's the lowercase letter sequence. You just get some sequence of A B C D A B C D E F G A B E G, long sequence, and then we run this thing that's basically a compression algorithm and it's a pretty, to do the full computation is a pretty slow process. The algorithms are written in C to run as fast as we could, and still for some songs it takes hours and hours because it's actually, it's using some optimization, like some dynamic programming techniques, but it's really effectively considering, every possible phrase grouping. And, the problem is, if you have A, B, C, D, A, B, C, D, the phrase, it could be that A, B is a phrase and C, D is a phrase, or it could be that A, B, C, D is a phrase. And you say, well, in that example, obviously A, B, C, D is better, but then later, you might have A, B, X, Y, so having a separate phrase to match that A, B might be advantageous. And so it really is an optimization problem, and we just basically crank it out and look at every possible assignments of phrases to sequences of measures, and take the one that works the best. And then and you asked about, so what if the music was actually structured so that there were repetitions of the melody, but the chords were altered in various ways, so and maybe not in interesting ways, so a human listener would just focus on the melody, and in that case, I think our methods would fail. I've looked at there are some really interesting sort of pattern discovery algorithms that look at multiple features and try to automatically pick the features that are giving rise to repetition, and I think something like that is happening when we listen to music, and it's a worthy pursuit for new algorithms and smarter systems. But I guess one of the advantages of, and I'll shut up in 1 second, one of the advantages of working with Pop 909 is it's all kind of very uniform and consistent, and so whatever methods you find that work on one song are going to work on all the other songs, but maybe not in general.
Just taking a look at the time, I think we actually have to get out of this room a couple minutes ago. I just want to say thank you very much, Professor Dannenberg, for giving your talk. This was lovely. And if anybody has any other questions, could they reach out to you via email, perhaps?
Yeah. Please feel free to email me. I think I'm easy to find.
Great. Well, with that, thank you again, and I hope everybody has a good rest of their semester.
Thank you so much to both Professor Dannenberg and the students here.
Happy holidays to everyone, and thanks.
Thank you, Roger. I'll recap.
Okay, great.